The Earth has experienced several ice ages throughout its geological history, characterized by the expansion and contraction of ice sheets. These cycles are not just historical, they are ongoing processes that shape our planet's climate. An ice age is a prolonged period during which global temperatures are significantly lower than average, leading to the formation of extensive ice sheets. The current ice age, known as the Quaternary Ice Age, began approximately 2.58 million years ago and is marked by cycles of glacial and interglacial periods. Understanding termination events is crucial in this context. Termination events refer to the transitions from glacial to interglacial periods and are typically characterized by rapid warming and significant changes in global climate. They occur in three distinct phases. Phase 1. A gradual increase in greenhouse gases, such as methane and carbon dioxide, leading to initial warming. Phase 2. A sharp rise in temperatures, often driven by a sudden release of greenhouse gases from natural reservoirs like permafrost and ocean sediments. Phase 3. Stabilization of the climate at a warmer temperature, leading to a new interglacial period. Recent studies suggest we may be experiencing a new termination event driven by human-induced climate change and natural processes. Evidence shows a dramatic increase in atmospheric methane levels over the past few decades, particularly since 2006. Methane, a potent greenhouse gas, is released from both human activities and natural sources, including tropical wetlands. As temperatures rise, these wetlands expand and produce more methane through decomposition processes, creating a feedback loop that can accelerate warming, similar to what has been observed during past termination events. Historically, the most recent termination event, known as Termination I, began around 20,000 years ago. It was marked by the rapid melting of northern hemisphere ice sheets and a rise in sea levels by approximately 120 meters. This event transformed vast areas of tundra into lush grasslands, supporting diverse ecosystems. By analyzing ice core and sediment records, scientists can draw parallels between past termination events and current climatic changes, offering insights into how quickly the Earth can transition from glacial to interglacial states. The mechanisms driving termination events are complex but critical for predicting future climate scenarios. Milankovitch cycles, which include variations in Earth's orbit and axial tilt, play a significant role. These cycles affect the distribution of solar energy received by the Earth, influencing glacial and interglacial periods. As ice melts, darker surfaces are exposed, absorbing more sunlight and further increasing temperatures, creating a positive feedback loop that can lead to rapid climate shifts. Recent indicators suggest we may be on the brink of a new termination event. The unprecedented rise in methane levels since the mid-2000s is a primary concern. Researchers link this increase to changes in tropical wetland dynamics, which may be exacerbated by climate change. Global temperature records indicate a trend of increasing warmth, with recent years consistently ranking among the hottest on record. This warming trend aligns with the initial phases of past termination events and raises critical questions about the future of our planet. The implications for human civilization are profound. Rising sea levels, changing agricultural conditions, and increased frequency of extreme weather events could threaten food security and lead to the displacement of populations. Understanding these dynamics is crucial for developing strategies to mitigate the impacts of climate change and adapt to a rapidly changing world. During a glacial period, massive ice sheets expand to their maximum size, covering vast regions of land and sea. Eventually, something causes this ice to start melting, marking the end of the glacial period. This process, known as a termination event, typically occurs in three phases. A slow but steady increase in global temperatures marks the beginning of the end of the glacial period. This process is often driven by changes in Earth's orbit known as Milankovitch cycles, which include variations in the Earth's angle and orbit around the Sun. The first Milankovitch cycle, Eccentricity describes the shape of the Earth's orbit, ranging from a perfect circle to a more elliptical shape. The Earth's current orbit is relatively circular, but more elliptical orbits lead to greater variations in solar energy received. This cycle has a periodicity of approximately 100,000 years and is well aligned with past glacial-interglacial transitions. Fall deglaciation, significant ice melting and sea level rise occur over a short period, usually decades. This phase is characterized by a rapid increase in temperatures, driven by the release of greenhouse gases like CO2 and methane from cold oceans or permafrost. This accelerates warming and reorganizes ocean currents. Interglacial stabilization. Following the rapid heating phase, global temperatures begin to stabilize, marking the onset of an interglacial period. During this phase, ice sheets stabilize and sea levels come into equilibrium. Negative feedback loops, such as the growth of vegetation in previously ice-covered areas and weathering processes that draw down atmospheric CO2, become more significant, stabilizing CO2 and temperature levels in the atmosphere. Methane levels have risen significantly in recent years, despite the temporary reduction in other pollutants during the COVID-19 lockdowns. Methane is produced from various natural sources, including wetlands, oceans, and the digestive systems of animals. It is a powerful greenhouse gas, trapping heat about 80 times more effectively than carbon dioxide. Methane's ability to absorb and emit infrared radiation, particularly at wavelengths of around 3.5 and 8 microns, makes its contribution to the greenhouse effect more pronounced. Recent advancements in technology have improved our ability to detect methane sources. For instance, NASA's Jet Propulsion Laboratory has mapped methane emissions using lasers tuned to specific wavelengths. This has identified major methane plumes, such as those from Iranian landfills and clusters of super-emitters in Turkmenistan. Methane emissions are increasing in tropical and wetland regions, driven by rising temperatures and CO2 levels, which enhance the decomposition of organic matter. Permafrost regions are also contributing to methane emissions as they thaw and release trapped organic material. Understanding these dynamics is essential for addressing the challenges posed by climate change and developing effective strategies for mitigation and adaptation.